Welcome to the deep dive. So if you're a data engineer who's making that jump over to AI, you've probably hit this wall,
Oh, absolutely.
this big mystery, right?
Right.
How do these LLM embeddings, these kind of opaque arrays of numbers, actually store semantic meaning?
Yeah, how does it know what an orange is?
Exactly. Today, we're going to try and open that black box.
And our mission, really, is to give you a kind of Rosetta Stone for this.
Okay.
We want to show that this abstract world of AI vectors is fundamentally built just like the SQL databases you already know, inside and out.
Okay, so let's start with an analogy. You call it the orange table.
The orange table.
Right. Imagine a simple SQL table. You've got one single orange, and that's one row.
Yep.
And it's defined by these descriptive columns. Let's say color, taste, this juice, size, and country.
A nice, clean row. Very straightforward. And here's the fascinating part. That definition, it's exactly how vector databases like QGrand are structured.
Wait, really? So that SQL table is what?
That's your vector collection.
And SQL row, the orange itself.
That's your vector. That's the array holding all the semantic data.
Okay, that's clicking. So the columns then, they have to be.
The dimensions, exactly. And the total number of columns you have, that's your dimensionality, the size of the array.
Right, which connects directly to something every data engineer lives and breathes, feature engineering.
It's the same core idea.
I mean, in SQL, you're always carefully choosing columns, maybe concatenating first name and last name, to create a new, better feature.
And really, you can think of an LLM as just a highly specialized feature engineer. That decision, which features to keep or transform, is why higher dimension vectors are just semantically richer.
So it's the difference between describing our orange with 5 columns
Okay.
versus, say, adding 12 more, like price per unit or expiry date.
More columns, more information, more meaning.
But that richness, it has to come at a price. What happens when our vector gets too long, when it has hundreds, maybe thousands of features?
You run straight into a very famous wall called the curse of high dimensionality.
And this is a huge problem in systems like retrieval augmented generation, RAG, where the model has to search for similar information.
A massive problem. The LLM tries to find vectors similar to your query, and it just struggles.
And sticking with our SQL analogy, finding similar rows is easy with 3 columns.
Trivial.
But in a huge table with 1,000 sparse columns, every single data point starts to look incredibly unique.
Exactly. The very concept of similarity just breaks down. The data is spread so far apart in that vast space.
It's like you're trying to find 2 identical snowflakes in a blizzard.
A blizzard is the perfect analogy. And the curse hits because so many of those 1,000 dimensions are actually redundant. They're measuring the same underlying thing in slightly different ways.
You need some kind of intelligent compression.
You do. And that's where a technique like principal component analysis, or PCA, comes in. You can think of it like a brilliant database architect.
So its function is to find that redundancy. It looks and sees that, okay, sweetness, sugar content, and glucose level are all highly correlated.
They're all telling you the same basic story.
And PCA consolidates them. It creates new summary columns that capture that essential pattern without needing all the originals.
And the result is it's transformative. PCA can take your table from 1,000 sparse columns.
The blizzard.
The blizzard, right. And it can reduce it down to maybe 20 or 30 consolidated, meaningful columns. And here's the key part.
It preserves the information.
It preserves about 95% of the meaningful information. So you've suddenly restored efficient, accurate similarity searches for the LLM.
So for you, the listener, the challenge is really to understand this balancing act. You need that high dimensionality for rich semantic meaning, but you absolutely need low dimensionality for efficient retrieval.
And PCA is the tool that makes that trade-off possible.
Which, if we connect this to the bigger picture, it leaves you with a really profound question to think about.
Yeah.
When PCA reduces all the complexity of language down to just 20 or 30 of these consolidated components, what are the fundamental hidden characteristics that those components actually represent?
And to take that one step further, how much of what we consider human-like reasoning is simply that? Just an incredibly efficient form of pattern consolidation built on that same kind of compressed structure.
Something to keep exploring.